Thank you. Thank you very much for having me. As I just said, it's not super late here, so thanks for organizing this seminar so early. So I have kind of a project in mind that I would like to discuss. It's really more like a project than one particular paper, and it's joint work, mostly in progress with quite a few people that are listed here. Hopefully my screenwriting is visible. And yeah, what I would like to explain is kind of the ideas that come up if you try to study, instead of representations of groups or representations of Lie algebras or representations of any kind of algebraic object you like, you study more like the categorical version. So you study representations of categories, which means essentially you replace the matrices you see in representations by functors and see what comes up. Basically, that's the idea. We'll talk about a little bit about the motivation, give you a lot of examples, and state one theorem. And the theorem is already spoiled here on the first slide. And my hope is, in the end, I will understand my little picture here. For now, it's just a picture, and we will get to the meaning of it during the talk. So what I really like to think about is that representation theory of categories, in some sense, is modeled along representations of categories of representations. So it's a kind of categorification in progress here, some kind of categorification going on, in the sense that classical representation theory, I will call it classical during this talk, is concerned about representations of groups and their categories as a whole. And I take the categories as a whole and study their representations. That's essentially the idea. All right, so let me give you some background here. So the whole story is actually motivated and very, very closely related to the representation theory of monoids and groups. I won't go into details just because I don't have time, but essentially this is my picture that I have in mind. So at the bottom slice of my cube, you see kind of classical representation theory. So you see groups and monoids, and at the back you see their representations, group representations, monoid representations. Group representations, amazing. Group representation theory is one of the most successful fields of mathematics from the last century. So it's essentially 120 years old by now-ish, roughly-ish. It has been extremely successful, turns up everywhere. The monoid version, so monoids are just groups without inverses, is less popular. It took a while to get started. It really got started here in the 1940s, so mostly by those people here. And it's actually almost as loose as group representation theory. It's of course a bit more complicated. You don't have inverses. Inverses usually help, but it's not much worse. And it seems to me like it's getting more and more popular as we go along. So group representations, classical applications of group representations are random walks and so on, so probability or something. And now probability theory catches up monoid representation theory as well. Same goes for physics, again, a classical field where representation theory is really applied. And roughly 20 years ago, which is very recent for mathematics, mathematics is so ancient that 20 years ago is very recent, there was this, people started thinking about categorical analogs, mostly motivated from physics, again, so from quantum algebra and quantum topology. So they had categorifications we have categorifications of groups, which people call fusion categories. So fusion categories. And we have categorification of monoids, and I will explain to you what those are, and we call them fiat categories. So we'll say in a second what the notion fiat actually means. So it's a shortcut for 4 different words here. And in the back, we like to study the representation theory of those categories. So essentially, they are those categories which are categorical analogs of groups. They generalize groups and monoids in a very particular sense. And we like to study their representation theory because, well, why do you like groups? Well, groups turn up in the wild as symmetries of some object. Same for monoids. Monoid is a little bit of a broken symmetry because you don't have inverses, so it's a little bit of broken symmetry. But essentially, groups and monoids live through their actions, so you should study the linear versions of them, and that's representation theory. So what we would like to do is just to do the categorical analog, motivated by examples from various fields of mathematics, mostly from mathematical physics, but also from knot theory and modular representation theory. So these are the classical fields where we apply this theory. but today I will only tell you about the theory itself instead of focusing on its applications. Okay. So by the way, feel free to stop me. Obviously, we are not a huge group, so if you have a question, just stop me and I will try to answer it. So categorify, let me just mention this, is a little bit like a philosophical notion. It doesn't really mean anything. So take everything, if I say categorify, it's more like take everything with a grain of salt. There won't be a precise definition. It's this idea of replacing step theory by category theory in some form that it makes sense to your project at hand. Okay. So what I would like to do is I would like to explain today really kind of the properties, what we see here, the main examples, the running examples. And I will discuss two examples in a lot of details. So instead of studying classical representation theory, representations of a group over whatever complex numbers you fixed field K, we study representations of the category of representations of a group. That's kind of the rough idea of a categorified representation theory. Again, categorified comes with quotation marks. And I will discuss two examples for you, which hopefully will make sense. Right. So here's a definition of a fiat category. We'll come back to that in a specific example in a second. But essentially, what I need to do is the following. So if you study representation theory, you need to specify first the object you want to represent, and also where you want to represent them on. So group representation theory looks very similar to representation theory of Lie algebras, for example, but then the details are different and will be the same on the categorical level. So I need to tell you very explicitly what I would like to study and where I would like to represent it on. And there are a few notions involved, which I come back later. I already have them on the slide here, but the main important one is in green. So categories should be roughly, the categories I study should be roughly like finite groups, finite monoids, finite dimensional algebras. There's something finite involved. And in my setup, this corresponds to having finitely many indecomposable objects in my category. So finitely many indecomposable modules. And there are some linearity assumptions, kind of the usual ones. It should be linear over some field, there should be some additive, and there should be direct sums. The main point is I would like to mimic finite dimensional groups, finite dimensional algebras, finite groups. So I put in some finiteness assumptions in my categories. We'll see that in action later. And I'm completely ignoring there will be a two-categorical version. There's even a three-categorical version of the total nonsense, but I'm not going into this. So monoidal is for me already kind of complicated enough for today. Monoidal is just saying that in the Grothendieck ring and the Grothendieck algebra, you actually have a multiplicative structure. So monoidal categorifies really the composition in a group. Examples that we will study examples, as I said, for the rest of the talk, essentially, but here's some list of examples. At least one of them will work for you. So, for example, the trivial group to study is a trivial group. Right? Well, that's the easiest group. What is the easiest category to study? It would be the category of vector spaces. That fits into my framework. It has one indecomposable object, the ground field itself. It's additive and whatever. And it's a monoidal category. So you can tensor representations, which in this case just means you can tensor vector spaces. It's really just a standard example here. Other examples are representations of a group, representations of a Hopf algebra, something where you can tensor your objects. But it's not necessarily restricted to those. It's just an abstract framework in essentially any category satisfying these conditions will be an example of what I would call a fiat category in a second. It's quite a big framework, okay? Quite a big set of examples. For example, if you like Hopf algebras, usually representations of Hopf algebras will be examples. Kind of depends where this condition is satisfied, but in the semi-simple case, for example, it's always satisfied. So if you like groups are included, Hopf algebras are included, and so on. Very good. All right, so let me try to motivate this story. So in representation theory, if you want to think of representation as being kind of matter in chemistry, so you like to study matter. That's just the point of chemistry, I guess. And at one point in chemistry, there is a decision, and you call certain things elements. You call them the elements of chemistry. You write down a periodic table. That already tells you quite a lot about matter in general. In representation theory, we do the same. We like to study representations in general. At one point, we make a decision to call some things elements. Turns out that in representation theory, you have essentially two choices. So either you call the representations without substructure, without subrepresentations, you call them the elements. These are the simple representations, or some people call them irreducible. It's a matter of taste whether you call them simple or reducible. I will call them simple representations in analogy to simple groups. They kind of play the same role. Or you say, okay, that sounds like a nice element. It's something without substructure, but because we have an additive structure, you can also say something is the indecomposables form the elements. So indecomposable just means you can't write a non-trivial decomposition. It turns out that these notions are not always the same. So in some sense, the simples correspond to the elements of chemistry, and the indecomposables correspond more to the compounds in chemistry. And they're usually not the same, right? In chemistry, an element is not the same as a compound. But they build everything, right? They build matter in general. And it kind of depends a little bit how on the flavor of representation theory you like to study. You either prefer one or the other, but you need to make a choice in general. And it turns out that in the setting I like, most examples prefer the indecomposables over the simples. So I would choose the indecomposables as my elements, which makes life a little bit more complicated, we'll see. But in the end, more examples will fit into the theory. Okay, so let's have a look at an example. Our good old friend rep G over some field. So just representations. G is always a finite group in this talk. So representations of a finite group over some fixed field. That's monoidal. You can tensor representations. Fancy language is the group ring is a Hopf algebra, right? So you can tensor representations of groups. It's linear. I just chose a field, right? So it's linear, it's additive, it's idempotent complete, it has finite dimensional Hopf spaces, and it has all the properties I want. So it's really kind of the standard example of the theory. So in case you ever forget the list of properties I want, keep that example in mind. If you just abstractly think about it, whatever properties this example has, I will put them on my list, essentially. Slight catch here, we'll discuss it in a second. Sometimes it actually has infinitely many indecomposable objects. We'll make a precise statement in a second. A very nice one, actually. And all this stuff here is what I call fiat respective finitary. So this just means, so F is for finite, I and A are for involution and adjunction, which means it has dualities. That's why this goes one step further than the other. So finitary is just everything's finite, and fiat is everything is finite and you have dualities. So finite dimensional vector space tend to have dualities, which is very, very useful. And so we include that in the theory. So fiat category is all that crap. And the finitary category is all that crap without necessarily having duals. And most of the theory works for those types of categories, meaning essentially everything. So it's quite a big class of examples. So linear, you can always kind of throw that in. That's boring. Additive is boring. Idempotent complete. So you can take direct summands, not just direct sums. Is also a fairly harmless condition. Most examples will have finite dimensional Hopf spaces. You can relax that condition a little bit if you want, if you're worried about finite dimensional Hopf spaces. But the really crucial condition is that you have finitely many indecomposable objects that corresponds on the categorified level as having a finite basis of your whatever algebra. So they have some finiteness conditions on the setting. And if you just think about the huge difference between representations of finite groups and non-finite groups, so infinite groups, they're really different. So for infinite groups, you usually have to throw in some extra conditions, which makes the game interesting in certain sense, but also more complicated. You want to study some topological properties or something. I'm staying here in the completely discrete world of everything is finite, and I don't need to worry about any analytic topological anything. Certainly, people think about the more topological versions for infinite categories in the sense, but I won't do that today. Right? It's my decision of staying essentially with some discrete mathematics, if you want. Okay, so here's my standard example. The only thing that might fail is this one, and I show you now an explicit condition what you can actually do. Okay. Just for completeness, if you would study a monoid, and that's why we have this difference between finitary and fiat, a monoid doesn't have inverses. The duality is built out of inverses. So rep of a monoid is usually usually doesn't have a dual. So monoid representations usually don't have dual representations. But monoid representations still fit into this framework of the first one, which is essentially everything. Yeah.
Sorry, so in the second case, S is the monoid?
Oh yeah, sorry. Yes, S is always a monoid and G is always a group. Fine. S, the notation S comes from that actually I should think about semi-groups, so I don't even need the unit. So semi-group is the same as the group without unit and without inverses. That's where the notation S comes from. Great. So S is a monoid. In general, this is not satisfied for a monoid, but still it fits into the theory. Kind of fun. So kind of really careful if you work with monoids. There you don't have duals because you need to take inverses, but you can't in general. Let me show you how that matters and make the precise statement. So let me the kind of the easiest group, not quite the easiest non-trivial group, but this one is pretty harmless. So Z-mod 5 cyclic group has 5 elements, and I take some funny field for this. So this is always harmless unless you take characteristic 5. Because in characteristic 5, you don't have any fifth root of unities. And usually what you would do is you would just write down the fifth root of unities, and it would determine for you 5 simple representations of dimension 1 by just sending the generator to that root of unity. In characteristic 5, you don't have root of unities. Why is that, actually? Because you have this miracle equation here, x plus 1 to the fifth. If you think about it, and you apply binomial theorem, you will see that all coefficients are actually divisible by 5, except the leading ones. So you don't have any non-trivial roots of unities in characteristic 5. Right? So all the binomials that turn up here will be divisible by 5. You think about the binomial theorem. So cyclic groups are always good unless you are in the defining characteristic of the cyclic group. And then something funny happens. So defining characteristic here is, of course, F5. I just take F bar for some, well, go to the algebraic closure because it's a bit easier to work with algebraically closed field, but the main features already happened for the element with the field with 5 elements here. In this case, you can actually check that the group ring is isomorphic to this beast by exactly using this equation here and sending the generator of the group to so sending 1 plus the generator to X. That's essentially what you do. 1 plus a generator sending to X will be 1 minus a generator. Well, I always get the signs wrong. 1 minus a generator will be of order 5, nilpotent of order 5. So we have this isomorphism to this truncated polynomial ring. And it's very easy to write down the indecomposable representations. They're given by the Jordan blocks in this case. So again, I only have 1 generator. I only need to tell you 1 matrix for that generator. And there are 5 indecomposable Jordan blocks, and they correspond to the 5 indecomposable representations of this category. In contrast, this has just 1 simple representation, namely the first one, because you have exactly 1 root of unity, 1 fifth root of unity, the trivial fifth root of unity, 1. But you have 4 other non-trivial Jordan blocks, and the Jordan blocks correspond to the indecomposables. And that's my difference between, that's how I would like you to think about the difference between the simples and the indecomposables. The indecomposables essentially correspond to Jordan blocks, and the simples correspond to roots of unities in some sense. In any case, I have 5 of them, and it's some Jordan block combinatoric to show that you don't have any others. Really easy calculation, not hard. It's a not hard calculation, not very hard. So this is actually an example of a fiat category. So in Z-mod 5 over characteristic 5. Okay. The second easiest group I can imagine is the Klein 4 group, which arises in Klein's picture or as a symmetry group of C squared, actually, of the cube with C squared in my little picture up here. And you can show the following. You can work over characteristic 2. Otherwise, again, it's not very complicated. In characteristic 2, the exactly the same argument as before. The group ring is isomorphic to a polynomial in two variables, right? Two generators, two variables, they both square to 0. And again, this is just one simple object because we have one primitive second order unity in this case, which is a unit. But it has infinitely many indecomposable objects. So you can actually write them down explicitly. So if you think about the generators x and y, and you just write them down on, well, this is an even and an odd. So you just have a vector space of dimension 2L. I just write the nodes for the basis vectors, and the action of x and y is what you see. So x sends 1 to then to the side and then to 0, because x squared is 0, y goes in the opposite direction. And as you can see, they exist for any L, so there are infinitely many indecomposables. These are the replacements of Jordan blocks in this case. So we have infinitely many indecomposable Jordan blocks for the client foregroup and characteristic 2, which is almost the easiest example you would ever write down. In particular, this one doesn't fit into my framework. Okay, and I will show you now a classical theorem which classifies all groups that work. It's a very classical theorem. It's called, well, it's due to Hickman. One of the two Hickman study representation theory. I'm never sure which one. In the 50s, one of them. I'm not sure which one, but it's very simple. So if characteristic of K does not divide the order of your group, you're fine. That's always good, right? In all of those cases, I decided to go for the different one. So 2 divides the order of my group. Obviously, 5 divides the order of my group. If that doesn't happen, you're always good. Huh? And if it happens, you're cyclic if and only, you have finitely many indecomposables if and only if, group theoretical property, the p-pseudo subgroups are cyclic. The p-pseudo subgroup of a cyclic group, in this case, is always cyclic. And you can write down the Jordan blocks explicitly. The p-pseudo subgroup of something like the client foregroup is the client foregroup itself, the 2 pseudo. So it's not cyclic. And there you go. You can always construct infinitely many. So these are not just random examples, these are prototypical examples. And you can build the general theory from those 2 prototypical examples. Okay, so you have finitely many indecomposables unless we are not in those cases. So you're unlucky, you hit a characteristic where the p-pseudo subgroup is not cyclic. Which then in practice happens all the time because pseudo subgroups tend to be not cyclic as soon as you get to bigger groups. Yeah, so you really can just list them. So if you're interested in rep S3 over F2, you just list. So this is a subgroup lattice of S3. The blue circles are the cyclic subgroups. So S3 has everything cyclic except S3 itself, I guess. And the green ones are the 2 pseudos. So all 2 pseudos are cyclic. They are Z mod 2 in this case just. So this one is good. So this one has finally many. Similarly, dihedral group with 10 elements. Careful, D5 dihedral group with 10 elements. It's always 2 times the number you see. The symmetry group of the regular pentagon, that's where the notation comes from. The 2 pseudos are all cyclic, and you're good. If you go to S4, so S4 was a bit too big to fit on the slide, so I just took A4, essentially the same, and you mark the 2 pseudos again. It will be the client foregroup, actually. This one is a non-example. For D6, so this is 12, then this is 6, and this is also the client foregroup. Again, it's not cyclic. So it's very easy. If you know the subgroup lattice, you just check whether the p-pseudo subgroups are cyclic. And you get a precise statement about the indecomposables in those cases. In particular, I said again, if you like complex numbers or something, you're always good. It's just a matter of playing with the characteristic here. It's a very complete statement. I like it a lot. It's very complete. Right? It's an if and only if. So let me skip this and let me show you another example. So the what I skipped is essentially there is no analog for monoids. So in case you're interested in monoids, I can't tell you a nice statement. So most of the time, monoid representations are really, really tricky and you don't know what's going on. So monoids in that sense are much, much harder than groups.
Another question?
Yeah.
So, of course, in the two cases, the first one is the case where the group algebra is actually semi-simple and everything is easy. Remind me, is the group algebra always Gorenstein, or is the second case the one where it's Gorenstein?
I think it's the second case where the one is Gorenstein, but I'm not 100% sure. It's not always.
So is Gorenstein on the rim side really what implies your finiteness condition?
It could be. I think that's right, but I'm not 100% sure. So don't quote me on this.
Okay.
So it's not always. Sorry, yes? Yeah.
And so if I take the monoid analog of the symmetric group,
yeah.
So like all maps from 1 to n to 1 to n.
This one here, right? End instead of odd. Yes. It's called the transformation monoid. Yeah.
This is precisely what I wanted to ask. So I wanted to ask whether this is finitely many positives.
Almost never. As you can see, almost never. So that's a good question. Okay. So monoids are really much more complicated. Already the analog of a symmetric group, that's your question, it doesn't have finite representation type. So finite representation type is the name for having finitely many incompossibles. Unless n is very, very small. So monoids in this regard is really complicated. It's really complicated. Okay. Another nice class of examples for people who like finite groups is what you can do. I just told you a precise condition for a finite group when the whole category works. It might not happen, but maybe you can make a subcategory work. So what I would like to discuss is you just take a representation out of your category and take its tensor powers and see what happens as a category. That usually is not the whole category itself, it's just a subcategory, and you might be lucky, but all the other properties are automatically satisfied anyway. So it's monoidal by construction because my new objects are just tensor products of a representation. It's linear, it's additive, all the other stuff comes for free. Whether it has dualities depends on the representation you've chosen, but it doesn't matter so much. Let me show you some very explicit examples. Let me cut this. So for example, you could take an old theorem due to Alperin basically, and then written up by Kovac. So you can take, here's a finite group. So SL2 over a finite field, that's a finite group. So my field here is FP to the K, right? So for some characteristic, and you can take any simple representation of that group, and the subcategory it generates is always fiat, which means it's always finitely many indecomposables that show up in the decomposition of those tensor products. Okay, let me give you an explicit example. So I could take P equals 5, field with 5 elements, and K equals 2. So actually the field with 25 elements. And if I run this, and it's very easy to run this in, this is done in Magma, it tells me that, so I take the 4-dimensional simple in this case. Why is it 4-dimensional? I take the square of F25 to 5, but my ground field is F5. So it's 4-dimensional over my ground field. Right? So F25 is 2-dimensional, and the representation itself is again 2-dimensional, so it's 4-dimensional. And I tensor it, I get whatever. I computed it by, in Magma, I get 45 indecomposable representations in total. The whole subgroup, as a whole group, we already know what to do. We just check for the pseudo subgroup in characteristic 5. And again, Magma can do this, so everything is very explicit. And it tells me it's false. So the whole category has infinitely many indecomposable objects, but my little subcategory here has only finitely many, 45 to be precise. And this works for any simple representations of SL2 in finite characters. Okay? So take a simple representation of SL2, your favorite one, tensor it with itself, you find finitely many indecomposables in its decomposition. So pretty cool there. Right? So I said again, the whole category, infinitely many indecomposables, it has pseudo subgroups that are usually not cyclic. The subcategory has finitely many. So even if you are unlucky and your favorite category doesn't quite fit, you usually can make subcategories work. It's an old example here. You're not so lucky. Yeah.
Sorry, can we replace the group here by the Lie algebra over the finite field? Or Do you know if this changes much?
This is still true for the Lie algebra. That's a good question. I don't think anybody has studied this. It's not automatically true. So they're quite different over the finite field.
Okay.
I don't know. I think nobody has studied this. It's a good question. It might be true.
Okay.
Just a warning here. So the way you usually go from the group to the Lie algebra is by differentiation, and differentiation over a finite field is complicated. So there is no very good relationship anymore between the group and the Lie algebra. That's why I'm hesitating to answer your question like yes or no, because I really don't know. That's a good question. Okay. Point here is, even if your favorite category doesn't work, a subcategory usually does. Here's another one, same flavor. So any two-dimensional symbol of any finite group works. Take its tensor powers, you will only find a finite number of indecomposables. Here's an explicit example, D6. We already had D6 here. So D6 is actually over in characteristic 2 a non-example. Yeah? But if you just take the subcategory generated by a two-dimensional representation and has one, that's what the first thing says. So it's not an example in general, but this one only has actually 3 indecomposable objects in this case. Okay? So any two-dimensional representation over any finite group actually works, and any field. So that's much smaller in general than the whole category. I haven't found a good reference, so I call this a folk result, but I don't know. Someone proved it apparently at one point in their lives. And there's a whole zoo of those. I don't think this is actually as studied as it deserves to be. Alperin calls them algebraic modules, so the ones for which the tensor power is has finitely many indecomposables, because having finitely many indecomposables forces the polynomial relation on the representation itself in its tensor powers. So you call it an algebraic, like an algebraic number. It's an algebraic representation, and it's like very like for algebraic numbers, there's a very sporadic results, like the two I showed you. But in general, I don't think there's a really worked out theory, and this deserves way more attention. For example, for your question, whether this actually works for Lie algebras or what you can do for Lie algebras hasn't been really studied, I think. I think also very hard.
So very stupid question. When you say we take these tensor powers, I mean, we do the idempotent completion, right? We take all sums.
It takes the indecomposable summands as well. And that exactly, because we take the indecomposable summands, we see finitely many of them. So the nth power, you will only see things that you have seen before. So the nth power will satisfy a polynomial equation, and that's why you call them algebraic modules. I'm not saying it's easy to write down the polynomial equation, but there will be some polynomial equation satisfied. There's a minimal polynomial. They're really just very sporadic results in this direction. Let me just mention one more. So if you're interested in the sporadic groups, you will get statements about the sporadic groups. So any symbol of the Mathieu group 11 characteristic 2 works again. Again, the whole category has infinitely many, but the Mathieu group itself has finitely many. Sorry, the tensor powers have finitely many indecomposables. And this goes on. So for any sporadic group, I can write down a list for you in some primes, but it's a very incomplete picture. In contrast to the Hickman theorem, which was a complete picture, this is kind of a very incomplete picture. It's essentially saying you can make a subcategory work, but you have to be really careful how you choose it. So if you're interested in some second monster group, you will find some primes where some representations of the monster group where it will work. For others, it's not known, and for others, it doesn't work. That's roughly how it goes. It's really like with algebraic numbers, right? So there's a zoo of statements about algebraic numbers, but really no kind of general result that tells you. There are always surprising examples of numbers where we don't know that they're algebraic. It's kind of the same here. So all other modules are, by the way, called transcendental, if that wasn't clear from my exposition. So I don't know any relationship between the sizes of those. So there are probably more transcendental modules, representations, than algebraic ones, but we don't know. Anyway, my point is all the algebraic ones, again, fit into the same framework of any Hopf algebra which satisfies the same, and so on and so on. Again, this question for monoids is kind of highly understudied, and there's essentially no theorem at all. But I would expect that certainly some natural modules of Hopf algebra, of monoids should be algebraic in this sense. Here's another one, the held group in characteristic 2, something happens, blah, 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 blah. Not so important to get all the details, just the overall flavor. It's widely open, but there's a certain, like for algebraic numbers, there are certain cases where we actually know quite a lot. Okay, let me, yeah.
We have flavors. So, of course, in general, one shouldn't hope that the monoid algebra of a monoid is the Hopf algebra, because you don't have the inverse.
That's correct. In general, it's not.
But can this happen? So, do you have an example where there is some near non-trivial?
So you mean not a group, and yet the monoid algebra is a Hopf?
Yes, with some non-trivial antipode.
And with the coproduct being all the monoid elements?
Yes.
No.
I think that can't happen exactly. No.
Yeah, okay. Yeah, okay. One we need to change. Yeah, right. One we need to change the quantification, and then it's not the thing. Okay.
Right, and then we can't tell, of course. But yeah, so the answer is no, as Uli said. So with monoids, it's really tricky because they're really not Hopf algebras. All right, let me do something different. Let me tell you a complexity measure on those categories, which are called cells. That's a classical notion in monoid representation theory, and it works as follows. It's an order on my indecomposable objects. And I say there's a left order, there's a right order, there's a right order, left ideals, right ideals, two-sided ideals, same idea. So I only tell you one of them. So I say two indecomposable objects, x and y. Everything here I write is indecomposable. Z is also indecomposable. One of them is left lower than the other. If you can find a representation that you can tensor to it, such that y appears as a direct sum. So I can go from x to y by tensoring with a representation. Then I call it left lower. That defines a pre-order, a partial order on the set of indecomposables. And the equivalence classes with respect to those orders are called the cells. So x is left equivalent to y. I give you some examples in a second, if and only if, well, this happens. This means you can go from x to y by multiplying with z, and you go from y to x by multiplying with z. You will find the other one always as a direct summand in your representation. And the H cells, I will have a nice picture for you in a second, are the intersections of the left equivalence classes called left cells, and the right equivalence classes called the right cells. But I have a nice picture for you. So essentially, it's the following idea. So every little box here represents an equivalence class of indecomposable objects, and I will start somewhere with a unit, and it will be ordered. So there's some order involved. As you can see, there's some partial order. And if you are within one box, so the big box is a two-sided one. So the big box here is a left-right cell. The columns are left cells, and the rows are right cells. So you order everything in a matrix-type fashion. It's really the same picture as for ideals. If you would apply ideals to your ring, you would end with left ideals, right ideals, two-sided ideals. You would end with intersections of ideals, which are those little H's. So those little boxes here, these are the H's. The notation comes from monoid representation theory. So you have left, right, two-sided, and H. Two-sided, the matrix block, left, the columns, right, the rows, and H is the matrix entries. And what it's saying is, yeah.
I think you should explain to people who don't know maybe the cells for monoids, like this in more detail.
Well, just to get the picture, right? I mean, so the L and the R was defined on the previous slide.
Yeah.
So this I've got. So there's a certain partial ordering.
Yes.
Okay, and on the page you now say
the partial order looks like a matrix. So your whole set of indecomposables by the partial orders, the left partial order is a bunch of matrix pictures, one for each partial order block, one for each equivalence clause, and within them you have left and right like a matrix. The left cells in the columns, the right cells in the rows, and the big ones are the two-sided cells.
So the matrix, so the red circled matrix
is one
you call
left-right cell, exactly.
One left-right cell.
Two-sided
and
cell.
The L, if you can go one slide to the definition of the, so I mean with the L, it's about tensoring on the left and then finding Y in there. With the R, it's on the right.
And with the left-right, it's on both sides.
Yes, left-right is both sides. And okay, but on the next, and this is on the next page, it's about the left-right. It's not about the equivalence class.
These are the equivalence classes, and because it's left, so the big boxes are the equivalence classes, and because the left-right is from left and right, it will partition finer into left cells and right cells at the same time. And the finer partitions are the columns and the rows.
So did you just, what's the monoidal category here? Or did you just take a, monoid?
This is not a monoidal category, this is just a general picture. I will show you a monoidal category in a second. In general, this equivalence relation partitions your indecomposable objects in a given monoidal category into matrix blocks of left-right cells whose the columns correspond to left cells, the rows correspond to the right cells, and the matrix entries correspond to intersections of left and right cells, which are the H's. Maybe it helps to have an explicit example. For example, what I would do is the following. I take rep S3 over complex numbers, very harmless. So I have three indecomposables, three simple modules, the trivial representation, the standard representation, and the sign representation. Trivial, standard, and sign. And the trivial representation will turn up as a direct summand of standard tensor standard. So in particular, the standard representation is lower than, so standard representation is left lower than the trivial representation, and similarly, standard representation is right lower than the trivial representation. And the trivial representation is also left lower or right lower than the standard representation, because it certainly turns up as a direct summand. The standard representation turns up as a direct summand of trivial tensor standard. So trivial is always very, very small. And this measures how far you are away from the trivial representation. Similarly for the sign representation. If you tensor it with itself, you see the trivial representation is a summand. So it's also left lower, right lower, two-sided lower than the trivial representation. So everything here is just very boring. It clusters in one block. So everything is equivalent here. So my matrix picture is very, very boring. It just has one block because everything appears, you can get everything by just tensoring from your representation. In general, if you have a duality, that's the definition of a dual representation. You will find a trivial representation as a summand. So by the definition, this is a direct summand. So it's left lower than the trivial one. So this is the trivial one. So and the trivial one is always left lower than everything. So it will end up in one cell. So as soon as you have some form of semi-simplicity and duality, so semi-simplicity will make everything split. And as soon as you have duality, everything just clusters in one cell, which in particular happens for all rep G over the semi-simple part. So the whole idea here is to have a an equivalence class on the indecomposables. It gives you finite information how the indecomposables relate to one another under tensor products. But in the semi-simple case, you don't have any finite information. Everything is just one equivalence class. That is just what happens in general. If you have some equivalence notion, you will eventually end up with some example where the equivalence classes are trivial. And it turns out that in this setting, I don't write down a precise theorem. It turns out that these are all. So the ones where cell theory is trivial are exactly the semi-simple ones with dualities. So essentially just those examples.
Let me stop. Wenn du Lehrer mal die zwei und alle Prinzipien von S3.
Ja, das meine ich.
Also das ist eine direkte Summe von allen.
Nee, also Vorteil ist die direkte Summe von allen drei Prinzipien. Okay.
Ja. Das? Sorry.
No problem.
Here's what you mean by standard. Now it's clear. Right?
Oh.
It could have been reduced straight.
In this case, it is, yes. The standard is n-1 dimensional of Sn, exactly.
Okay, very good.
Correct. It's not the regular one, it's a standard one, but okay, it's n-1 dimensional.
Okay, cheers.
Yeah, due to reasons of time, let me just skip the rest and just jump to an example. Oops. Okay, so what I would like to study are representations of those categories, and what I will use is the part I skipped, or briefly explained, and I will write down the theorem in the end. We'll talk about the theorem, but first, let me tell you about representations of categories. So representations of a category is just a functor to a nicely behaved other category. So I would need to specify my target category, and I make the decision that what I like to act, that should be the same as what I would like to act on. So my target category should be of the same flavor, this finitary stuff. So representation is then just a factor from, let's say, rep G to, for example, endomorphisms of rep G. And an example would be just the tensor product factor. So you can tensor representations that defines you an endo functor of your category. And that's an example of a categorical representation of this beast. And if you look, for example, what happens in the Grothendieck ring, in this example of S3 again, the standard representation, the two-dimensional one, if you look at the tensor product, so this just says that standard tensor trivial is standard, so you just write it in the matrix. So here's the standard representation, here's a trivial representation, here's a standard one, and here's a sign representation. Oh, very good. So standard tensor trivial is standard, so I write a one here. Standard tensor itself is a direct sum over all of them, so I write one in every entry. Standard tensor sign is again standard, so I write this matrix. And similarly for the other ones, this one might make more sense. So sign representation behaves like an anti-diagonal matrix. So sign tensor trivial is sign tensor standard is standard, sign tensor sign is trivial, and the trivial representation is like the identity matrix. So on the Grothendieck level, you see those matrices. On the categorical level, it's the tensor product functor, right? So just M goes to the functor of tensoring with M. And that's an example of a categorical representation of one of those categories. So instead of having a group set it to a vector space, I take one of the group representations and I send it to an endo functor. And I would send, that's kind of this picture here, I would send a morphism to an intertwiner. So in this case, really just the F tensor intertwiner. It's a functor. It's a whole piece of information. Here's another one. So same setup, but now I take a subgroup and I can write down a tensor functor from rep G to rep K. So it's an endo functor of rep K, right? Rep G is fixed, rep K is on the other side. It's an endo functor of rep K, which is given by restriction. So you can restrict a G module to a K module and then tensor with it, and that gives you an endo functor on the category of K representations. K, right? This case of subgroup. So restriction is another example. Yeah.
If I may ask a question, if you go back to the last slide.
Mm-hmm.
Okay, so do we understand this category? So endofunctors of C, or like so because you said on the Grothendieck level it would be like this. I mean, it makes sense because well, I have these well indecomposable objects or simple objects, and then I can say where they go. Like, can I really imagine endofunctors? Yeah, okay, I guess this makes sense. The C as a category is just 3 copies of K vector spaces, right? It's K vec plus K vec plus K vec in this case. And then are just matrices.
That's right.
Integer entries, maybe.
Everything here is semi-simple, yeah, exactly.
Yeah. Okay. Okay, so this, I answered my own question. Okay.
That's very convenient. In general, this is hard. In general, we don't understand the end category on the right-hand side. Absolutely not, yeah. Right. So tensoring is a representation. Restriction is a representation. And essentially, one of the classification theorems, one of the first ones you would write down are, these are all representations. So there are no, these are all simple representations in a sense. There are no other representations. Let me give you a precise statement. So what you can do, I will ignore this slide for a bit. So we have seen, well, the first one is just the one for G equals K. So I only showed you exactly one. So the restriction factor. Since this is a category, what you can still do is you can twist the monoidal structure in a very precise way. I don't want to go into details. I've put it on the slide just for completeness. You can twist the monoidal structure by a cocycle, a certain algebraic object. Doesn't matter so much. Point is, on the Grothendieck level, these categories are exactly the same as the ones we saw before, but the monoidal product. So the action itself is twisted by, and a cocycle is just a scalar on the representations. So you can twist everything by scalars. Fine. But I want to note here that we have now those guys here, one for each K given by restriction, and there's some twist of the monoidal structure involved. Okay. And it turns out that in this example, that's it in a very precise way. So let me just put up the statement. So an old theorem here, so a simple categorical representation is just a representation without substructure, exactly as before. Turns out that studying indecomposable representation is essentially hopeless. So on this level, I want to restrict to simple representations. And all simple representations of any finite group of rep G over complex numbers are always of the form, take a subgroup and restrict, and potentially twist the monoidal structure. And they are the same. It's a really complete statement. They are the same if and only if the subgroups are conjugate, and there's some condition on the cocycles to be conjugate as well. In particular, you can write down a complete list of them for any given group, which is a complete classification in this case, which is actually, note that this is actually better than the classification of simple representations of a finite group. In some sense, or it's very similar. For a finite group, you would write down the conjugacy clauses, and for each conjugacy clause, you have a simple representation. Here, I write down the subgroups, and for each subgroup, I essentially have a simple representation. It's a very similar statement. It's actually kind of cute. So endofunctors of the representations, functors from the representation category of a group are determined by subgroups and twists. It's a very cool statement. So this is how it looks like in practice. So if you take S, so let's ignore S4. S4 gets a bit more complicated, but this is a combinatorial problem. So for S3, the top, you just list the subgroups up to conjugacy, and we already did that. And each one of them turns out to, so this H2 is the obstruction set for the twists. It turns out to be trivial in this case. So in this case, you have 4 simple representations, 1 for each subgroup. And I've written down the ranks for you. So 1, 2, 3, 3 in this case. Anyway, and in general, you just do it. It's just an algebraic kind of a combinatorial problem. You look up your favorite list of subgroups of finite groups, So here's S4, has a certain number of subgroups. You count them up to conjugacy. For example, this appears twice. This also appears twice. So each one will spit out a simple representation. And here you have non-trivial cycles. So this one will spit out actually 4 simple representations, 1 for each conjugacy clause and 1 for each cocycle. So you just list everything. It's a very, very nice statement. So for RepG, actually everything is known in that sense. This classifies functors from RepG, and it's a really nice classification, a very simple one in terms of subgroups and some algebraic data given by a twist, by a scalar, essentially. And the algebraic data is not mysterious. I again just looked that up on a page about groups. So you'll find people have calculated this group cohomology, in case you know group cohomology. People have calculated all of these already in the 50s, the 40s of the last century. It's a very explicit statement. That's great. That's RepG is easy in this case. I'm working over the complex numbers here. So if you're wondering about the other ones, the characteristic P ones, statements, well, we know the statements, but they get much more complicated. So functors are classified by subgroups. That's essentially what I'm saying, which is a really ridiculous statement. If you think about it, just from the outset of this problem, classifying certain types of functors from RepG to something, it seems to be pretty hopeless, but you get such a nice answer in this framework of those categorical representation theories. An amazing answer. As I said, it's comparable to the simple representations of a finite group correspond to conjugacy clauses. Okay, let me just wrap up and tell you what you do in general. So essentially what I'm saying is that this is the case you need to know, and all the rest is built out of the others. Is built out of this. So in order to not go too much over time, 2 minutes left, let me just state the main theorem. Let me just make it like this. So in general, you do the following. You have this picture here. Let me just go back to the picture. Whoop, too many slides. Let me try to find it. Come on. The matrix picture I was trying to tell you about. So for a general category, you compute those equivalence clauses. That's essentially a problem of decomposing your representations, which is not necessarily trivial, but it's not a categorical problem. It's a problem of decomposing representations. And you get this picture in the matrices. And the main statement is that each matrix block will correspond, will give you a certain number of simple representations, and corresponding to the little matrix blocks, which are essentially almost always RepGs. So you get a classification of those pictures in terms of those equivalence clauses. Write down those equivalence clauses, a combinatorial problem or a decomposition problem. You get simples associated to the matrix blocks, and you know exactly how many simples you get. And they're essentially classified, again, in the same spirit as RepG. So essentially what I'm saying is, the general picture is, here's some category of this flavor, and I call the category S, and this is the equivalence class on the set of indecomposables. And all of these little blocks here essentially correspond to something like RepG. A category is built out of those little RepG blocks. And the classification problem for functors from your category reduces to classification problem of functors for each of those matrix blocks. And that is a complete classification of the functors. And for all of these matrix blocks, I'm lying a little bit. It's not always RepG. It can get more complicated, but essentially the categories of the form RepG, at least in almost all examples, were written up. So this gives you a classification of functors for an arbitrary category of that type if you compute decomposition numbers and know the answers for the little blocks. And that's why in the very beginning, I had my picture like this. If it loads, so file apparently is too big. So the general category will be of this type. And for each matrix block, I need to pick a subcategory. And the simples are in one-to-one correspondence with that subcategory. And that's kind of the main statement in the theory. So the I will finish in a second, then you can ask your question. Just one sentence. So the general picture is for a general category, you compute the decomposition numbers, decompositions, you get this cell structure, and each cell block gives you a certain number of simple representations corresponding to smaller subcategories that live in your picture. Okay, I'm already 1 minute over time, so thank you very much.